if you really want to get comfortable with loops, you have to write a lot of code. So to get you to practice writing code with loops, let's try and write a function to calculate e to the power x using this classical Maclaurin series expansion. Now, obviously, if you really want to calculate e to the power x, you should check in the library of C if there is such a function. And indeed, in math.h, there is this function exp to calculate exactly what we want. But let's ignore this because our focus here is to practice. Now, this is an infinite series, and obviously we cannot calculate to infinity, but we will, limit the series to the first n terms. So let e of x comma n be the sum of the first n terms of this infinite series, and we'll try and write a function in C that takes these two arguments. X is a real, so we'll represent that as double, and n is some integer, and we will return a real value, again a double. Now, you've seen a few functions with loops, so it won't surprise you that if we want to calculate the sum, we will keep a variable, an accumulator, that we initialize to 0, and we'll keep adding into this sum as we get new terms, and then finally we will return this sum. So what should the loop look like? Well, we have a sum starting with I equal to 0. And remember, we have to calculate n terms starting with I equal to 0. So if we want to calculate n terms starting with I equal to 0, we have to go up to I strictly less than n, meaning I will take the last value n minus 1, and then we'll be still in the loop. And then when I increases, I will become n, and we will stop the loop. So this is again fairly standard. You will see this kind of code written lots and lots of times. This is a standard way to get a loop to run n times, and you will get so comfortable with it, you will start writing such code automatically. And sometimes you have to be careful because this is not the right code in every case, but it'll certainly do this loop body n times. Now, what do we want to do in the loop body? We want to increase the value of sum. Sum is accumulating the answer. So we can use that plus equal to operator. And if you look at the formula that's given in the Maclaurin series, the term is x to the power I. Well, we have a function power x comma I. We just wrote it. We even had an optimized version of it. So we can use that in the numerator. And there is I factorial in the denominator, so we have to write an I factorial function. A function that will calculate the factorial of a given integer. So here is a good opportunity for you to practice this code. Why don't you pause the video and think about how you're going to write this function, and then we'll continue the video and you can see the answer. Okay, so here is my attempt at writing the factorial function. So once again, I'm going to have some sort of variable to accumulate the answer, and we'll set it up, and finally when it's done, we'll return the answer, and then we'll write a loop. Now I want to be careful here. I want to calculate, in this case the parameter is n, so I have to calculate n factorial. And n factorial is 1 times 2 times 3 up to n. So once again, there are n things that I want to multiply, but I won't write the loop starting with I equal to 0. I'll start the loop with I equal to 1, and I will do I less than or equal to n, because those are the values of I that I want to multiply out. I want to multiply 1 times 2 times 3 all the way up to n. So each time in this loop, whatever the value of I is, I multiply the current value of answer by I. So just like we have a plus equal to for addition, we have a times equal to for multiplication. This just means the new value of ans is the current value of ans times I, and I do this and I get my answer and I just return it. So do you think that this is correct? I wouldn't have asked that question unless there is something fishy here. So why don't you take another pause at this video and see if you can find the bug in this little factorial function that I've written. So the error is in how I have initialized the ans variable. if you see, I have just, without really thinking, I have initialized ans to 0. And if I initialize ans to 0, then inside the body of the loop, we have the new value of ans is old value of ans, which is 0, times something. Now 0 times something is always 0, so this function is always going to return 0. Right? And if you have to think about this a little bit carefully to realize that you have to initialize ans to 1. So that's our overall function. Now let me just show you how it runs, and just so we get comfortable with using it. So I have written the function already. I'm going to go to the command line this time and just run my program. I have a main that asks me how many terms n do I want in the series, and helpfully it has used the definition of the exp function in math.h to calculate e to the power 1. So that is 2.718, etc., etc. And now I'm using my my e function that I have defined to calculate e to the power 1 to n terms in the series. So suppose I say n is 2, I only have 2 terms in the series. It says the calculated value, if you only add the first 2 terms, meaning I equal to 0 and I equal to 1, then you'll just get the answer 2, and that's off by 0.718. I mean, we're several digits away from the true answer. If we increase the value of n, we look at more terms in the series, you see that our error becomes smaller and smaller and smaller. So you get the idea that the more terms you use, we are off by a smaller and smaller amount, and in the limit, as n tends to infinity, this will approximate, this will reach the exact value of e, so e to the power 1. All right, so that seems quite nice, and we seem to have this very simple function. It uses, you notice, these two other functions, power and factorial. These are sometimes called helper functions. I mean, maybe our main goal was to write this function e, and we needed to use these other functions, power and factorial, and so we wrote those as helper functions to help our main goal, which was this function e. So this seems very nice, but there are two problems with this. So problem number one is it's really slow. And if you look at the way in which we have written the code, right? I mean, the main part of the code is this for loop that is repeatedly calculating the next term to add to the sum variable, right? We want to add the next term into the accumulator. And really, this seems very wasteful, because for each value of I am computing x to the power I from scratch, and I'm computing I factorial from scratch, right? I mean, if you think about I factorial, that is 1 times 2 times 3 all the way up to I. Now, in the next iteration, I will want to calculate I plus 1 factorial, and that's just another one more term to be multiplied, right? And similarly with the numerator, x to the power I plus 1 is just x to the power I times x, right? So really, if I recognize that the I plus first term that I'm adding into the sum is just the ith term times x in the numerator divided by I plus 1 in the denominator, I should be able to save a lot of time. So we will make this change in the next video. But first, for this video, I just want to point out that our existing code is a little bit slow, and we can certainly optimize it by making use of this observation. But there's a second problem, and the problem is much worse. Not only is our code slow, it's wrong, right? And let me explain to you why it's wrong. So if you look at this summation, right? I mean, I'm talking about x here being 1. I'm calculating this summation, and all the terms in this summation are positive terms, right? So this summation is going to approach the true answer e to the power 1 from below, right? I'm going to this is a strictly increasing sequence, and it's going to always be, for any n, if I calculate this, the answer is always going to be smaller than the true value of e. Remember, I'm only doing this calculation for x equal to 1 in the code that I have showed you, right? And what you can see in the code that I have showed you is that for each value of n, the true answer is smaller than the uh, true value of e. Now, this is of course also an approximation of e, but you notice that all these answers are smaller than this. This is the best approximation that I have to represent e using a double, right? And so each of this off by is just calculating the true answer minus the calculated answer. And you notice that all of these are positive numbers, right? So as I increase n, I'm going to get smaller and smaller errors, but they're always going to be positive, right? Because I'm always adding positive terms, and there are more terms to add, which I'm currently ignoring because I'm only doing n terms out of an infinite possible set of terms. But here is something very strange. So if I calculate up to 13 terms, I get this very small error. Now I want to be greedy. I want a 14th term, right? So I want to get even closer. And you notice that I have actually calculated a value that is beyond the true value of e, or the closest approximation to e that I have. And my error is negative. This is telling me that I have exceeded the value up ahead and up above, and you can confirm by looking at the digits very carefully that this is 284 over here, whereas this is 288. So I have exceeded that. So this is very, very strange. I have this piece of code that is somehow exceeding the infinite series, even though I've only calculated it to 14 terms. So this is a puzzle. I really want you to think about why this is happening. It is subtle, and you really have to think about it very carefully. And it's one of those things that you may not be able to completely reason about just in your head. You may actually have to look at the code and try and follow some of the values that are there, and maybe even print these values out, or use something like Python tutor to look at the values of these terms as they are being calculated, and perhaps you will be able to see the error. In any case, we'll discuss it as usual in our next video.